Hello students, I am Dr. Aruna Palta. Today we will be discussing a very useful topic which I think everyone should know about. I hope all of you will agree with me that without fats and oils, cooking is not possible in our kitchens. But how many of you know about the rancidity that develops in fats and oils if they are not stored properly? And lastly, what are the good storage practices for maintaining them in good conditions for use? So let us now go on a knowledge tour through this module to know about rancidity and storage of fats and oils in the subject food science. The objectives of this module is to know what rancidity is, to learn about the mechanism of rancidity, to understand the factors responsible for rancidity, to understand the role of antioxidants, and lastly, to know about the good storage conditions of fats. Stability of a fat or fatty acid is significant to maintain a fresh taste or odor during storage and use. The stability is related to the composition of the fat moiety and the changes it is subjected to. Fats with substantial unsaturated fatty acids are usually unstable. The presence of agents causing oxidation, which we call as pro-oxidants, or preventing oxidation, which we call as antioxidants, and the methods of storage determine their stability. Vegetable fats are usually more stable than some of the animal fats, such as lard, even though the degree of unsaturation of the vegetable oils may be greater. This is attributed to the presence of natural antioxidants in them. The food products undergo changes in flavor due to the chemical changes occurring in fats and oils present in them. The causative factors responsible for such a change are atmospheric oxygen, presence of enzyme, and application of high temperatures. The change that a lipid undergoes, leading to an undesirable flavor and odor development, is known as rancidity. This is brought about in two ways: hydrolysis and oxidation, giving rise to hydrolytic rancidity and oxidative rancidity, respectively. The figure below indicates that when a triacylglycerol, that is a fat, undergoes oxidation in the presence of lipase enzyme and water, it is converted into glycerol and free fatty acids. These free fatty acids only are responsible for the bad odor of any fat or oil. Hydrolytic rancidity occurs when the fat is broken up into free fatty acids and glycerol in the presence of water. Hydrolysis is catalyzed by acid, bases, enzymes, or thermal effects. When base is the hydrolyzing agent, the liberated fatty acids are converted into their salts, and the hydrolysis is termed as saponification. The other agents release free fatty acids, and the reactions brought about by them are collectively known as lipolysis or hydrolytic rancidity. The presence of the enzyme lipoprotein lipase quickens this process. In this figure, it is evident that when any fat undergoes partial or complete hydrolysis, then the ester bonds are hydrolyzed with the action of enzyme, heat, moisture, and free fatty acids are liberated. Diacylglycerols, monoacylglycerols, or glycerol is formed, and a bad odor is obtained after this hydrolytic rancidity. So this figure is indicating the development of rancid flavor in milk and also the bad flavor which occurs in fat after deep fat frying. Stop. Rancidity in foods may be very slight, indicated by a loss of freshness, to very severe, indicated by objectionable odors and flavors. Hydrolytic rancidity occurs chiefly in raw milk due to hydrolysis of milk fat resulting into release of short-chain fatty acids. The flavor of rancid milk is due to even-numbered fatty acids from C4 to C12 and is not just due to butyric acid as common people believe. Free fatty acids are absent in the fat of living animal tissues but are formed by the enzyme action after the animal is killed. The temperature of rendering animal fats are capable of destroying the enzymes responsible for hydrolysis. Foods fried in such oils exhibit browning, cracked surface, and show increased fat absorption. After lipolysis, the free fatty acids form polymers, the viscosity of the fat increases, the color darkens, and the quality of the fat deteriorates. This is known as polymerization. Polymers decrease the heat transfer efficiency of oils and also affect the quality of products fried in it. Lipolysis can cause changes in fats and oils which can be minimized by the proper handling. On the contrary, in some foods, lipolysis is done deliberately to develop a typical flavor. For example, in different varieties of cheese, yogurt, and bread, controlled lipolysis is used. In the oil of oilseeds, a substantial amount of free fatty acids are present at the time of harvesting only due to hydrolysis. So, the oilseeds require neutralization with alkalis after they are extracted. Lipolysis seriously degrades the quality of frying oils as large quantities of water is introduced in frying oils from the food along with the high frying temperatures. The smoke point of a fat is seriously depressed due to lipolysis. For example, the smoke point of cottonseed oil decreases from 232.2 degrees centigrade to 160 degrees centigrade in the presence of only 1% free fatty acids. Now we will see what is oxidative rancidity. Oxidative rancidity is associated with the degradation of fat by oxygen. The double bonds of an unsaturated fatty acid can undergo cleavage through a free radical process, releasing volatile aldehydes and ketones. The fat oxidation process resulting in rancidity begins immediately after the animal is slaughtered and the muscle fat, intramuscular, intermuscular, and surface fat become exposed to oxygen of the air. This chemical process continues during frozen storage, though more slowly. The same thing happens with vegetable oils also. Now we will understand the mechanism of oxidative rancidity. The mechanism of oxidative rancidity has been extensively studied. Rancidity takes place through auto-oxidation because the rate of oxidation increases as the reaction proceeds. Oxidation takes place through a free radical chain mechanism involving three stages. First, initiation, that is formation of free radicals. Second, propagation, that is free radical chain reaction. And third is termination, formation of non-radical products. In initiation part, hydrogen is removed from the fatty acid chain to yield a free radical. The removal of hydrogen from the fatty acid chain takes place at the carbon atom next to the double bond and can be brought about by the action of light, metal, etc. For example, in oleic acid, The reaction will proceed by removal of hydrogen from carbon 8 or 11, resulting in free radical. In this formula, R is the free radical and this is converted into R and H when the initiation part starts. Once a free radical is formed, it will combine with oxygen to form a peroxy-free radical, which can remove hydrogen from another unsaturated molecule to yield a peroxide and a new free radical. This is called propagation reaction. This reaction may repeat up to several thousand times and takes the shape of a chain reaction. In the reaction given below, we can understand that the free radical is combining with oxygen to form peroxy-free radical. And this peroxy-free radical is again combining with RH, that is one more molecule of fat, and it is converted into ROOH, that is the peroxide, and one free radical is again removed from this cycle and it again goes to combine with oxygen to form a new peroxy-free radical. If the free radicals react with themselves to yield non-active products, then the propagation reaction is changed to termination reaction. This is well evident from the equation given below. The hydroperoxides formed in the propagation part of the reaction are the primary oxidation products. They are generally unstable and decompose into secondary oxidation products, which include a variety of compounds. Among the secondary oxidation products, aldehydes and alcohols form an important group. The volatile aldehydes are mainly responsible for the oxidized or rancid flavor of fats. This figure is depicting the mechanism of three-stage oxidation process of lipids. Any fat or lipid molecule, when it comes in contact with heat, light or metal, it gives free radical. This free radical combines with oxygen to produce peroxide, and this peroxide again combines with a new fat or lipid molecule to produce hydroperoxide, and again a free radical is produced. This free radical again gives peroxide, and this peroxide again goes to react with a new fat molecule. Meanwhile, in the form of secondary products, aldehydes, ketones, acids and volatile compounds are formed, and these compounds only provide bad odor and flavor to the fats and oils. Dear students, now we will discuss the factors which have a bearing on lipid oxidation. Many fats and oils, they undergo a change in flavor before becoming rancid. This change in flavor, which is very different from the rancid flavor, is known as reversion. In reversion, the flavor may be buttery, beany, fishy, grassy or painty. Food lipids contain a variety of fatty acids that differ in chemical and physical properties and also in their susceptibility to oxidation. In addition, foods contain numerous non-lipid components that may also oxidize and interact with the oxidizing lipids and their oxidation products. Oxygen concentration, temperature, and moisture are the other factors influencing autooxidation. The factors which affect lipid oxidation, amongst them fatty acid composition is the first factor. Fats and oils are made up of fatty acids. The number, position and geometry of double bonds within the fatty acids affect the rate of oxidation. Cis acid oxidize more than their trans isomers, and conjugated double bonds are more reactive than the non-conjugated ones. Auto-oxidation of saturated fatty acids is extremely slow. At room temperature, they remain practically unchanged when oxidative rancidity of unsaturated fatty acids become detectable. At high temperatures, however, saturated acids can undergo oxidation at significant rates. Now we will see the effect of surface area on lipid oxidation. The rate of oxidation increases in direct proportion to the surface area of the lipid exposed to air. In oil and water emulsions, the rate of oxidation is governed by the rate at which oxygen diffuses into the oil phase. Now we will see the effect of oxygen concentration on auto-oxidation of fats. When oxygen is abundant, the rate of oxidation is independent of oxygen concentration, but at very low oxygen concentration, the rate is approximately proportional to oxygen concentration. However, the effect of oxygen concentration on oxidation rate is also influenced by other factors such as temperature, surface area, moisture, and pro-oxidants. Now we will see the effect of temperature on the oxidation of lipids. In general, the rate of oxidation increases as the temperature is increased. Temperature also influences the relation between rate and oxygen partial pressure. As the temperature is increased, changes in oxygen partial pressure have a smaller influence on the oxidation rate because oxygen becomes less soluble in lipids and water. Now, let us look into the effect of moisture on lipid oxidation. In various fat-containing foods, the rate of oxidation depends strongly on water activity. In dried food with very low moisture content, oxidation proceeds very rapidly. Increasing the moisture content to a little extent retards lipid oxidation, and this protective effect is believed to occur by reducing the catalyzing activity of metal catalysts. At somewhat higher water activities, the rate of oxidation increases again, presumably as a result of increased mobilization of catalysts and oxygen. Now, let us look how pro-oxidants they affect lipid oxidation. Transition metals, particularly those possessing two or more valency states and a suitable oxidation reduction potential between them, are effective pro-oxidants. Examples of such metals are cobalt, copper, iron, manganese, and nickel. In concentrations of even as low as 0.1 ppm, they can decrease the induction period and hence increase the rate of oxidation. Trace amounts of metals are encountered in fats from soil where oilseeds are grown, from animals in case of animal fats, and from metallic equipments used for processing or storage of fats and oils. This is the picture where it is quite evident that how extra virgin olive oil is oxidized and it is converted into normal olive oil. When olives are procured from their farms and carried to the plant where oil is extracted from it, then with the effect of heat and sunlight, the extra virgin olive oil which is extracted there, it is oxidized into normal olive oil. And when it reaches the customer after oxidation, it loses its quality, and instead of extra virgin olive oil, we are getting only normal oxidized olive oil. Students, now we will learn about thermal decomposition of fats and oils. Both saturated as well as unsaturated fats undergo chemical decomposition when they are heated in the presence of oxygen. Their color, flavor, and nutritive value is altered. A large number of new compounds are formed like cyclic and acyclic dimers, long chain alkanes, aldehydes, ketones, etc. This figure is depicting the thermal decomposition of fats and oils. Fats and oils, either saturated or unsaturated, when their thermal decomposition occurs, then they are converted into acids, hydrocarbons, propanediol, acrolein, and ketones. This happens with saturated fats. And in the presence of oxygen, these saturated fats, they give long chain alkanes, aldehydes, ketones, and lactones. Similarly, the unsaturated fat after thermolytic reactions produce acyclic and cyclic dimers, and in the presence of oxygen they give volatile and dimeric products of auto-oxidation. All these end products, they give flavors which are known as rancid flavors only. Now we will see the role of antioxidants in the prevention of deteriorative changes in fats and oils. An antioxidant is a substance that is added to fat or fat-containing foods as a preservative to retard the oxidative breakdown of fat. An antioxidant should be fat-soluble, effective in low concentrations, and should not contribute any objectionable flavor or color to the fat or foods to which it is added. Antioxidants combine with free radicals, interrupting the free radical chain mechanism. Literally, hundreds of compounds, both natural and synthesized, have been reported to possess antioxidant properties. Natural antioxidants include polyphenols like flavonoids, ascorbic acid, that is vitamin C, and tocopherols, that is vitamin E. The natural antioxidants tend to be short-lived, so synthetic oxidants are used when a longer shelf life is preferred. Synthetic antioxidants include BHA, BHT, TBHQ, propyl gallate, and ethoxyquin. Again, antioxidants can be categorized as primary antioxidants and synergists. Primary antioxidants operate directly to inhibit autooxidation by donating a hydrogen to the free radical, thus breaking the chain reaction. For maximum efficiency, primary antioxidants are often used in combination with other phenolic antioxidants or with various metal sequestering agents. Synergists are compounds that prolong or enhance the antioxidant action of primary antioxidants. Now we will learn about some common antioxidants in fats and oils. The first one is tocopherols. These are the most widely distributed antioxidants in nature, and they constitute the principal antioxidants in vegetable oils. A relatively high proportion of the tocopherols are present in crude vegetable oils, which remains in sufficient quantities in finished oils to provide oxidative stability to the final products. Butylated hydroxyanisole, which is commonly known as BHA. It has found wide commercial use in food industries. This is highly soluble in oil and shows weak antioxidant property, particularly in those oils which are rich in natural antioxidants. It is relatively effective when used in combination with other primary antioxidants. BHA has a typical phenolic odor that may become noticeable if the oil is subjected to high heat. Tertiary butyl hydroquinone, commonly known as TBHQ. TBHQ is also moderately soluble in oil and slightly soluble in water. In many cases, TBHQ is more effective than any other antioxidant in providing oxidative stability to crude and refined polyunsaturated oil without problem of color or flavor stability. The graph given below shows that in crude soybean oil, TBHQ is showing the best induction time, and this is true for refined soybean oil also. Measurement of oxidative stability. Oxidative stability is a measure of a fat's resistance to oxidation. Because the process takes place through a chain reaction, the oxidation reaction has a period when it is relatively slow before it suddenly speeds up. The time for this to happen is called the induction time. There are a number of ways to measure the progress of the oxidation reaction. One of the most popular methods currently in use is the Rancimet method. The Rancimet method is carried out using an air current at temperatures below 50 and 220 degrees centigrade. The volatile oxidation products, largely formic acid, are carried by the air current into the measuring vessel where they are absorbed in the measuring fluid, which is distilled water. By continuous measurement of the conductivity of this solution, oxidation curves can be generated. The cusp point of the oxidation curve, that is the point where a rapid rise in the conductivity starts, gives the induction time of the rancidity reaction, which can be taken as an indication of the oxidative stability of the sample. Students, now we will discuss about storage of fats and oils. Fat should be stored in a cool place, covered and away from strong odors. They should be packaged to prevent oxidation. Oil should be stored at ambient temperatures in sealed containers. Once a container is opened and fats come in contact with air, the shelf life is reduced. Therefore, opened containers should be used relatively quickly. Once rancidity develops in fats or oils, they cannot be made palatable. Brown rice, wheat berries, or any whole grain flour contain the germ and bran, which has a lot of fat and creates further challenge for long-term storage. Low-fat beans, they store longer than high-fat ones. Nuts go great in cans, but nothing can stop the oils in them from developing rancidity over time. That's why every precaution has to be taken while storing whole grains and high oil content foods. In addition, rancidity can be controlled to some extent but not completely eliminated. The ways to slow down rancidity are the very same general rules used for all foods in long-term storage. The first one is keep it cool, the second one is keep it out of sunlight, and the third one is to keep it out of oxygen. Now we will talk about the packaging and shelf life of fats and oils. Solid fats and liquid oils are often sold in cans, plastic bottles, or pouches. Oils are rarely sold in glass containers anymore. Metal cans are the most resistant to long-term oxygen transfer. Plastics are not that resistant to oxygen transfer and will allow significant oxygen levels into the container in 1 to 2 years. All fat or oil products experience deterioration even when handled and stored under ideal conditions. Oils that do not require heating to remain liquid resist deterioration more than the higher melting products. Most shortening and other similar products will maintain an acceptable flavor and oxidative stability for 2 or 3 weeks in melted form with adequate controls. This table is depicting the shelf life of different types of fats and oils. Butter in open condition can be kept in a refrigerator in best condition for 2 to 3 weeks. Similarly, in unopened condition, butter can be kept in a refrigerator for 1 to 2 months, while it can be stored in freezer for almost 9 months. Vegetable oil opened remains in good quality in a pantry for 1 to 3 months. Vegetable oil unopened can remain in good condition in a pantry for even 6 months. Salad oil opened can remain in a pantry for 2 months. Similarly, salad oil unopened can remain in a pantry in a good condition for 3 months. Margarine, after opening, can be kept in refrigerator for 1 month, and unopened margarine can remain in best condition in a refrigerator for 4 to 5 months and in a freezer for almost 1 year. Peanut butter opened will remain in good condition in a refrigerator for 6 months, while it can also be kept in a pantry for 2 to 3 months. Peanut butter unopened will remain in the pantry in good condition for 6 to 9 months. Vegetable shortenings will remain in refrigerator in good condition for 6 to 9 months, while it can remain in good condition in a pantry for almost 3 months. Olive oil is quite sensitive for storage. It can remain in pantry for 1 to 2 weeks in good condition, and I would like to add that olive oil can become rancid quickly at room temperature, but it develops fat crystals in the refrigerator. However, olive oil can be stored in the refrigerator and allowed to thaw. Now we will talk about care of fats and oils. Fats and oils are used in many preparations as a cooking medium. If adequate care is not taken while heating and storing fats, it may result in deterioration of fat as well as of the food prepared using such fat. Some points should always be kept in mind while handling fats and oils in the kitchen. Do not overheat fats as they decompose at high temperature. Cover the fat when left in the deep fat fryer and ensure that the temperature does not exceed 200 degrees Fahrenheit. Follow a time and temperature chart for frying food. When fat has to be reused for frying, replace with equal quantity of fresh fat. That fats and the fatty phases of food take up flavors and odors of other foods stored nearby. So fats should never be stored near odorous substances. Copper or iron containers should not be used for storing fats. Glass is the best option. Salt speeds up while sugar slows down rancidity. This figure is depicting the ways to prevent rancidity. This can be done either by refrigeration or by storing fats and oils in dark places. Even vacuum packaging can help us. Then using inert gases in packaging. And lastly, by using antioxidants, we can definitely prevent rancidity in fats and oils. Dear students, now we come to an end of this module. I would like to repeat some salient points of this module. Lipid oxidation is one of the major causes of food spoilage. It is of great economic concern to the food industry because it leads to the development of various off flavors and off odors, generally called rancidity, in edible oils and fat containing foods, which render these foods less acceptable. Autooxidation is the chief reaction involved in the development of rancidity. This takes place through free radical mechanism consisting of 3 steps: initiation, propagation, and termination. It is influenced by fatty acid composition, oxygen concentration, temperature, surface area, moisture, and pro-oxidants. Hydrolytic rancidity occurs when the fat is broken up into free fatty acids and glycerol by the presence of water. This reaction is catalyzed by acid, bases, enzymes, or by thermal effects. Antioxidants are added to retard the oxidative breakdown of fats and thus preventing spoilage of foods. Literally hundreds of compounds, both natural and synthesized, have been reported to possess antioxidant properties. Fat should be stored in a cool place, covered and away from strong odors. They should be packaged to prevent oxidation, because once rancidity is developed in fats and oils, they cannot be made palatable again.